Okay, in the tutorial today we are going to look at how we can add joints between objects in physics. That combines with physics, so joints only have a meaning if you have the physics enabled, and they connect to objects in a flexible way, so they can still move a little bit with respect to each other, rotate, but they don't have complete freedom. So it's very different from, for example, a parent-child relationship, where objects are fixed in a fixed position with respect to each other. With joints, they can still move a little bit. Joints can also break. If you apply too much force to a joint, it will break. And joints can have motors connected to them, so that make them move. You can make a joint rotate over a certain amount of degrees, or you can make it rotate continuously, like a wheel. I'm going to illustrate that with a simple model of a robot, only 6 components: a body, 2 legs, 2 arms and a head. And later I will also add feet to make it a bit more stable, otherwise it will fall over. But let's start with the body. The body is a box. I prepared the code here so it doesn't take me so much time to type it. The body is a box, 1 meter high, 40 centimeter wide and 10 centimeter thick. I put it on a position where normally your body would be, more or less 1.7 above the floor. The center of the body is 1.7 above the floor, and it's a Collide box, so it has physics properties. If we run this, of course what we see is that the box falls down to the floor. There's no floor yet, but it falls down because there is nothing to hold it up. Later I will add a ground. I will add legs below the body to keep it upright, but for now I'm going to keep it on a fixed position using a joint, a special type of joint which has no degrees of freedom, so it just keeps the object where I want it to be. How can we add joints? Well, that's the vis.vis package, and there we have a choice between a number of different joints. I will now choose the fixed joint to keep it on a fixed position. A joint is meant to connect 2 objects. In this case I have 1 object which I want to keep on a fixed position in the world, so then instead of a second object I specify none, which means the world. So in this case the body is connected to the world with a fixed joint, and by doing this we will see that it does not fall down anymore, but it stays where it is. I want to add legs below the body, left and right leg as a cylinder, and also a Collide object, an object with physical properties. If we start with the leg on the left side, it's a cylinder of 1 meter high and 0.1 radius. I put it on this position on the lower left part of the body, and yeah, it has some friction here which is not that relevant. I can remove it. If we run it, of course the leg will fall down because it's not connected to anything. It just has gravity, so it falls down. I want to connect it to the hip using a hip joint. Same vis.vis, add hinge joint, leg left and body are connected. I also have to specify the position of the hinge. So now we see it does not fall down anymore, it stays there in a fixed position, and it can move forward and backwards because of this hinge. How can we illustrate this movement? Well, for that I'm going to add a little bit of code that when I press the P key, it will check the object under the mouse, it's the pick command, and that object will get a force into the world. I'm using the screen to world function to define a line, and along that line we have a force, small duration. So then we can see the effect of the hinge. Now I'm pressing the P key and we see it rotates. Actually it can make a full rotation if I press a few times. Applying the force once is not enough, but I do it a few times, it makes a full rotation. What you also can see is that the physics engine Invisit is really not as good as it should be, because this leg, when I rotate it, it moves through the body. You can see it go through the body. That should not happen, because both of them have a glide box around them. So they should collide and not go through each other, but yeah, for some reason the physics engine allows this. You see that I gave the joint a name, but we will see later why that is. In the same way I can add the other leg, which is exactly the same, slightly a different position. This one is to the right, this one is to the left, but they both have the same degree of freedom. If I apply a force here or here, you can see them swing. These hinge joints, next to defining a position, if I don't do that, I can show that if I forget to define the position, which I now did for the left leg, the leg on the left. You can see it appears as if the leg still falls down, and then we have a complete crash of the whole engine. In this case the position of the hinge is in the origin, but the body itself is 10 meters in front of the origin, so it has to make a really big turn. The leg is rotating around the origin, but it's a 10-meter radius rotation, and apparently the physics engine is not capable to deal with that. But if you do it in the right way, it looks okay. What we can also do is, this is rotation around the x-axis. If I give it a push, you see the rotation is forward and backward, so around the x-axis. The x-axis is going from left to right. I can change that. I can redefine axis 0, and I can say, well, I want the rotation to be around the z-axis, for example, 001. I did that for the left leg. If we run this, then when I push this leg, you see nothing happens, almost nothing. This one swings normally, but this one does not swing forward and backward anymore. It can only swing sideways. So if I would move myself to the side of the robot and give it a push in this direction, you see then it swings. And this one still swings only forward and backward. So you can define the rotation axis yourself, but the default one was fine, forward and backward, so we leave that. In the same way I can add arms also as cylinders, as joints, the left and right arm. Same height, a little bit smaller radius, position at the shoulder, a glide box. Yeah, this friction again, it's not that relevant, let's just remove that. And they both have a hinge joint on the right positions. And we can swing these arms also forward and backward. They're lighter than the legs, so it's easier to swing them. To complete the robot, we also have to add a head, which is a sphere object, put on top of the body. So that's this code. Of course, as you can imagine, if I do this, the head is now on top of the body, but it's just balancing there. If I give it a little push, whoop, it falls over. There's no connection to the body. I did not add a joint yet. By the way, the sphere is not completely round. I scaled it a bit to make it more like a head. It's a bit higher than it is wide. But there's no joint yet, so it's completely not connected to the body. If I want it to be connected to the body, I have to add a joint for the neck. In this case I choose a ball joint, which allows rotation in all directions. So we connect the head and the body, and the head can rotate in all directions around this point. So if I push it, well, it can rotate a little bit, but it bumps into the body right away, so that's why it does not move too much. If I put the head a little bit higher, and I push it, then you see it falls over, but it stays connected to the body. And same if I do that sideways. Push it in this direction, it falls over, but yeah, it bumps into the body, and it ends up in this position. But it has 3 degrees of freedom. It can rotate around 3 axes, also around its own axis, but of course in the sphere you don't see that. Yeah, so here we see 3 types of joints: a fixed, hinge, and a ball. And next we are going to add motors. Motors will work on a joint to keep the joint in a certain position. Like for the head, if we want to keep the head in an upright position, we have to add a motor to the joint, which will try to keep the joint at a certain angle. In this case, it should keep the head at the angle 0 in all directions. Well, let's add these motor forces. That's why we had to give the joint a name, because if it has a name, then we can say set motor angle, which will try to keep each axis, 0, 1 and 2, the x, the y and the z axis, on a rotation of 0 degrees, using a torque. A torque is like a force for rotation, a torque of 0.05 in this case, and the speed of 1. So then if we push it, the head should, with a spring, it should come back to its 0, 0, 0 position. So now pushing the head, well, it doesn't come back, so apparently this torque 0.05 is too small. Let's change that to 0.15. And push it a few times. You can see the head swing, but this is still not enough torque. So let's say 0.2. If I push it, you can see it swings a little bit forward and backward. And if I push it a lot of times, like I did now, you can see the head swing. But it comes back to its upright position because of these motors that I added. And since I added motors for all angles, also when I push it sideways, it will still come back to its original position. It's not a fixed joint, it can move. If you apply force, it moves a bit, but it tries to keep each angle at 0 degrees. I could, for example, change this into 30. Then the motor will try to keep the head in this position. And again, we see perfection of the Visit engine. It is not stable. Maybe it's touching the glide box of the arm or of the body. I don't know exactly what's going on. But if I push it, it also moves forward and backward. But yeah, this is one way to use a set motor angle. It's like a kind of spring that pushes the object back into its desired position. In the end, I want to make my robot walk, so I have to apply also forces to the hips. And I gave these joints also names, so I can say, well, this one should have plus 20 degrees and this one should have minus 20 degrees. Then you see it's like one leg forward, one leg backward, and again if I push it, it moves, but it always comes back to that position. It's not fixed, it can move. Yeah, when you really want to make the robot walk, then yeah, you have to make the legs move forward and backward. Of course, when we try this the robot is still hanging with his body fixed to the world here. If I remove that joint, it will fall down. But I can add a floor, a ground. So let's see what happens if we put the robot on the ground. So let's add a ground first, and the ground plane, of course. And let's remove this fixed joint. Well, the robot stays where it is, but of course it's not stable at all. It just falls over. One of the reasons that it falls over is that the hip joints are not, they don't have any motor, so they can freely move, and yeah, the tiniest disbalance will make the robot fall. So I could, to make it more stable, I could add again a motor to the hips to keep the hips at a zero angle, straight position. And then it will not that easily fall over by itself anymore. You see it's not perfectly stable, but it stays upright. But the slightest push, of course, will make it fall over. Boom. But the legs are still straight because of that motor. To make the robot more stable, I can add feet below the legs, like in this code. So over here I had a small box for a foot, 10 centimeter high, 35 centimeter wide and 70 centimeter long, position right below the leg, by itself a collide box, and connected to the leg with a hinge joint. Take care to define the right position. As you see, they already have motors. If I would remove the motor, same for the foot right, then it still falls over easily. One small push makes it fall, because there's no force at all to keep for the connection between the foot and the leg. By adding these forces, these motors, they will try to keep the motor, the foot and the leg in a 90 degrees relation. So the motors will try to keep the foot perpendicular to the leg. So they will not fall over that easily anymore. They will still fall over, but not with one push. I just pushed it. It still stays there. If I give it a number of pushes or higher, then it falls, still falls. But not as easily as before. Still trying to keep the legs straight. So now we have a robot which is quite stable. I can still push the arms, so they don't have any motor, so they can rotate freely. If I do it too much, it will fall over, but not yet. Yeah, there it goes. I might try to make the motors stronger. The hip motor now has a torque of 0.1, which is not that much. If I make it 0.5, it will probably stay upright longer. I'm now still pushing it. You see it bends, but still doesn't fall. And there it goes. Well, our final goal is to make the robot walk. Well, that's quite easy. I can add other motors to the hips to make the legs move forward and backward, alternating. Quite a bit of code. Not that difficult. So I will just add it in one go. We have function walk left, which puts, well, I think the right leg forward and the left leg backward. And this function walk right does the opposite. And in the walk function, I call them alternating. So first walk left, and then walk right, and then walk left, and then walk right. Connected to a timer. 1 second interval. So in 1 second one leg will go forward, the other backward, and then a second later the opposite, and in that way the robot moves. You see I also played with the friction. The foot which is supposed to go forward, I give it 0 friction, and the other one, the foot that's going backward, I give it a little bit of friction. If I wouldn't do that, the robot would not come from its position. So let's see. I connected it to the W button, so I press W now. And we see the robot quietly move forward. It's not 100% stable. If you wait, it will probably fall over after a while. But yeah, I didn't mention it yet, but I also added a motor on the ankles. There it goes. Keeps on moving, of course. I also added a motor on the ankles, this one, to keep the feet flat on the floor. If the leg moves forward, you don't want the foot to come up in this position, but the foot should stay on the floor. That's why I added this motor angle for both feet. Same here. Let's see what happens if I don't remove the friction. So now both feet have a non-zero friction, and when we start walking, well, it doesn't come from its place and it falls over immediately. So it's quite essential to play a little bit with this friction. Movement is quite random. It will, each time it will walk in a different direction. The moment that it falls over is different. But at least it walks. And just for fun, and on the occasion, because of the occasion that The Walking Dead Season 6 started this week, we can add some textures and colors. And actually it's a bit of a zombie-like movement, so it's not that strange to turn it into a zombie. Okay, that's it. Thank you for your attention.